Hi, I'm Marco, and this talk will represent domain-independent road machines for modular integration of planning and learning. In this work, we're interested in the integration of planning and learning. Such integration has several advantages, such as benefit from both high-level reasoning and low-level adaptivity to the underlying environment, improved sample efficiency of the learning problem, and the decomposability of the tasks that allow to reuse the learning policies in the new tasks. In particular, we're interested in the interaction of symbolic planning and reinforcement learning. Among related works, there are the classic option framework, in which the agent can learn a meta-controller of macro actions. The main limitation is that options need to be explicitly modeled, and the option definition is tied to the low-level state space. Another idea proposed in Precup and Kudenko in 2008 is to use plans to drive the reinforcement learning agent via reward shaping. A problem with this approach is that the resulting learning policy is not decomposable and cannot be easily transferred to new tasks. Another related work is the one of reward machines proposed by Kate et al. In 2018, where additional rewards specified by finite state machine improve the sample efficiency of the learning problem. The drawback of this approach is that the automaton must be manually specified and that an explicit mapping between the low-level and high-level representations is needed. Here, we propose a modular framework made of two separated and decoupled modules, the planning module and the learning module. The planning module computes the optimal plan for the task, and the reward machine is automatically generated from it instead of being manually written. The reinforcement learning module learns an optimal policy, maximizing the received rewards both from the environment and from the reward machine. Crucially, there is no explicit relationship between the state spaces of the planning module and the learning module. The framework is similar to taskable reinforcement learning proposed by ENS et al. In 2020, but ours allows greater decoupling between the planning and learning modules. The planning module receives in input a deterministic planning domain and a goal, and computes a plan that reaches the goal using an off-the-shelf planner. This step is done offline before the learning process. As future work, the planning module could also monitor the environment and recomputes the plan if there is a need. The reward machine is automatically generated from the plan by first transforming it into a transition graph and then by adding rewards on the transitions, such that the optimal policies aim to reach the goal. The reward machine works online together with the learning module and drives the learning process in two ways. First, by giving additional rewards to the agent, and then by informing the agent of the possible macro actions available, but only if the current state has changed. At each step, the reward machine observes a new high-level state from the environment. Then it updates its internal state and sends a reward, the current state of the machine, and the following states available, as said before. The learning module directly interacts with the environment as any reinforcement learning system, but it is driven by the information coming from the reward machine. The module is agnostic with respect to the specific reinforcement learning algorithm that is being used. The module can use the information about the available options to improve the learning. Moreover, the state space of this module is decoupled from the one of the reward machine and the planner. From the learning module's point of view, the setting is the same over restraining bolt proposed in De Giacomo et al. In 2019. We can rely on a previous result that shows that the agent only needs to keep track of the restraining bolt state and the low-level features in order to comply with the specification, if the environment allows it. The high-level features are hidden from the agent. In other words, this means that both components are independent with each other and can be designed and implemented separately, allowing the system to be highly modular. Interestingly, the automatically generated automaton transitions can be seen as subtasks, and such information can be exploited to improve the sample efficiency of the method. For instance, we could have exploration policies specific to each subtask, like variable epsilon in epsilon graded policies, or a probabilistic choice based on the success rate of the transition between two consecutive states of the machine. Or we could have a meta-controller of options that chooses the current best available macro action, observes the total return from an automaton transition, and updates the Q function of the meta-controller. Finally, the subtasks can be reused to achieve different goals. As a first example, consider the classical taxi environment. The taxi agent has to move on a grid, pick up a passenger, and drop off him to a specific location. The planning domain only models three types of interactions: go to a specific location X, pick up the passenger at the current location, and drop off the passenger at the current location. The learning domain, instead of having the macro action go to X, it can only move cell by cell in the grid world. In this slide, it can be seen as a simplified version of the taxi planning domain for the sake of the presentation. The fluents in this domain are P at X, meaning that the passenger is at location X, P on T, meaning that the passenger is in the taxi, and D at X, meaning that the final destination of the trip in the current episode is X. On the right, it can be seen the explicit grounded planning domain with all the possible moves. In the beginning, the passenger can be either at the red or the yellow location. The destination is always the green location. The states in red are the two possible initial states, and the state in blue is the goal state. The two sequences of arrows are the plans for two different tasks. At the top is the one that requires to pick up the passenger at location red and drop him off at the location green. And at the bottom is the one to pick up the passenger at location blue and drop him off again at location green. Note that the yellow state is shared between the two plans, and this means that it suffices to learn an optimal sub-policy only from one of the two tasks, in particular the one labeled with drop-off G at the bottom left, and reuse such sub-policy when learning from all the other tasks. We also considered an environment with more complex control, like breakout. We consider the task of breaking columns of bricks in a particular order. The planning domain only models the removal of the columns, whereas the learning domain handles the power control and sensing. On the plot, there are shown some experimental results when using the usual restraining ball setting, the red curve, and when considering automaton transitions as options with automaton-based exploration policy, the blue curve, as suggested earlier. The result shows that there are benefits in terms of convergence rate in exploiting the macro actions with smarter exploration policies. We also consider the Sapientino environment, a grid world in which a robot has to list colored cells in a certain order. The planning domain only models high-level moves, whereas the learning domain models the low-level grid movement controls. The plot clearly shows the advantage of using options. Also, in a similar environment like this simplified Minecraft, we could experience the same advantages when using a new approach. So in this work, we propose a framework that provides a modular integration of symbolic planning and reinforcement learning. The two modules are decoupled and independent, yet, if the environment allows it, the agent can learn the optimal policy. The result is a sample-efficient and decomposable modular approach. As a future work, we would like to adopt non-deterministic domains, which means the reward machine is not just a sequential plan, and then have the planning module to work online together with the learning module. Moreover, we can explore the possibility to refine the planning domain during the learning. Thank you for your attention.